Hi, I am Dr. Abhijit Muli from Department of Chemistry, Sadhguru Gadge Maharaj College, Karad. In last lecture, we have seen introduction about spectroscopy, what is electromagnetic radiation, what is electromagnetic spectrum, and effect of these electromagnetic radiations on your matter. In this video, we will see the first basic tool of organic spectroscopy, that is ultraviolet spectroscopy. The first slide shows the image of ultraviolet spectra. On y-axis it is absorbance, on x-axis it is wavelength in nanometer and the lambda max of 395. Now, what is ultraviolet spectroscopy? The absorption studies carried out using ultraviolet radiations are called ultraviolet spectroscopy. What is the region of ultraviolet radiations? It is 100 to 400 nanometer. In that, 400 to 200 nanometer is called as near ultraviolet and 200 nanometer to 100 nanometer is called as far ultraviolet. Now, all the commercial ultraviolet spectrophotometer use lower wavelength of 200 nanometer because measurements below 200 nanometer are extremely difficult. Ultraviolet and visible radiations, they are highly energetic. In first lecture we have seen the electromagnetic spectrum, in which we say that these ultraviolet and visible radiations, they are energetic, so they can produce electronic transition, that means transition of valence electron from lower to higher energy levels. Hence, ultraviolet or visible spectroscopy is often called as electronic spectroscopy because in these spectroscopies electronic transitions takes place. Now, main thing to remember is that ultraviolet spectroscopy gives information about unsaturation in a molecule. What is the use of ultraviolet spectroscopy in organic chemistry? It gives idea about the unsaturation in molecule. Let's see instrumentation in ultraviolet spectroscopy. First part is source, which is deuterium or hydrogen lamps. Next comes monochromator. What is the role of monochromator? If we want light of specific frequency, specific energy or wavelength, monochromator is used, which is usually prism or grating. Next is sample holder, that is cuvettes in which your sample is kept, that are quartz or fused silica cuvettes made up of NaCl or KBr for UV spectroscopy. Then is the detector, which is photomultiplier tubes. We are well known with these photomultiplier tubes. And last one is output, which is electronic or computer in advanced double beam ultraviolet spectrophotometers. Usually the output is computer. Then in introduction we say that ultraviolet radiations causes electronic transitions. And what are these types of electronic transitions? Let's see what are the types of transitions. First one is sigma to sigma star. What is this sigma to sigma star? Promotion of electron from sigma bonding orbital to sigma star antibonding orbital is nothing but sigma to sigma star transition. Since the sigma bonded electrons, they are strongly held, energy required for these transition is quite large. Since energy is large, energy is inversely proportional to your wavelength. Shorter wavelengths below 150 nanometers are required for these types of transitions. Now, what type of molecules show these type of transitions? Saturated hydrocarbons. Saturated hydrocarbons shows these type of transitions, that are methane, ethane. Next electronic transition is pi to pi star. Pi to pi star transitions. Promotion of electron from pi bonding to pi star antibonding orbital is pi to pi star transition. Now, compounds containing multiple bonds, that is carbon-carbon double bond, carbon-oxygen, carbon-sulfur, carbon-nitrogen, etc. undergo sigma to sigma star transitions. As pi electrons are delocalized, transition occurs at longer wavelength. Less energy is required for such type of transition, pi to pi star. Next comes is n to sigma star transition. Here, promotion of electron from n non-bonding orbital to sigma star anti-bonding orbital occurs. Compounds containing lone pair of electrons, that is usually heteroatom contains lone pair of electrons which are not used in bonding. They are having n non-bonding electrons, that is compounds containing lone pair of electrons on heteroatom like nitrogen, sulfur, oxygen, chlorine, bromine, iodine, etc. undergo such type of transition. A compound is shown, example is shown in this slide, in which your molecule contains a heteroatom which is singly bonded, contains lone pair of electron. Transition of these non-bonded electrons from n non-bonding orbital to sigma star anti-bonding orbital is shown in the figure. And the last transition is n to pi star transition, n to pi star transition, in which promotion of electron from n non-bonding to pi star, there is a mistake in this slide, pi star anti-bonding orbital. Such type of transition occurs in which compounds containing multiple bonded heteroatom, so that there is non-bonding electrons, that is lone pair of electrons on heteroatom, and there is also pi star anti-bonding orbital. Since there is pi bond in your molecule, there is pi star anti-bonding orbital, and hence there is possibility of transition of n non-bonding electrons, lone pair of electrons of heteroatom, from n bonding orbital, non-bonding orbital, to anti-bonding orbital, pi star anti-bonding orbital. Energy required for such type of transition is very low, so absorption occurs at longer wavelength. Now let's see the energy changes sigma delta E involved in different transitions. In the sequence sigma to sigma star, they are highly energetic transitions. Then comes n to sigma star, then comes pi to pi star, and then least energetic transitions are n to pi star. Sigma to sigma star transitions occurs by absorbing radiation in far ultraviolet, while the least energetic transition n to pi star occur by absorbing radiation in near visible region. So usually ultraviolet spectroscopy gives idea about unsaturation in your molecule. Let's see some important terms used in ultraviolet visible spectroscopy. The two main terms are there in this spectroscopy. First one is chromophore. What is chromophore? Chromophore is unsaturated group of a molecule that undergoes n to pi star and pi to pi star transitions. These two transitions are important to us, n to pi star and pi to pi star, since these two transitions absorb energy in near ultraviolet. Compounds containing chromophore are called as chromogens. Then what is the definition of chromophore? They are unsaturated groups in a molecule that undergoes pi to pi star and n to pi star transition. Let's see the examples. In alkenes, CH double bond CH2, this is chromophoric group. Then in alkynes, it is C triple bond C. Since it contains pi bonding orbitals and pi star anti-bonding orbitals, by absorption of energy, electron from pi bonding orbital can be transmitted to pi star anti-bonding orbitals, hence they are called as chromophores. Next, carbonyl compound, in which carbon double bond oxygen, this unsaturated species carbonyl group is chromophoric group. Next, in azo compounds, N double bond N, in which two types of transitions can be possible. One is pi bonding orbital to pi star anti-bonding orbital, since there is pi bond. And next one, nitrogen contains lone pair of electron n non-bonding electrons to pi star anti-bonding orbitals from the pi bond. Next group is nitroxo group, in which the chromophoric group is N double bond O. Last one, nitro group, N double bond oxygen. So this is about chromophore, which is unsaturated group and causes N to pi star and pi to pi star transition. The next important term is auxochrome. An auxochrome is atom or saturated group containing non-bonded or lone pair of electrons. What is auxochrome? It is atom or saturated group. There is no unsaturation in this, containing non-bonded or lone pair of electron. By itself, it does not absorb radiation greater than 200 nanometer wavelength. But when this auxochrome is coupled with chromojoin, that means when it is attached to a molecule which contains chromophore, it shifts the absorption towards longer wavelength and increases the intensity of absorption. That means auxochrome itself doesn't absorb radiation, but when it is attached to chromophore, it shifts this absorption towards longer wavelength and also increases the intensity of absorption peak. Some common and important auxochromes are OH, OR, SH, Cl. Look, in all of these groups, they contain lone pair of electron. In OH, there is lone pair of electrons on oxygen. In OR, again there are lone pair of electrons on oxygen. Sulfur, chlorine, nitrogen, all of them contains lone pair of electron. They itself doesn't absorb, but when they are attached to chromophore, they increases the lambda max value. Then auxochrome offers its lone pair of electron for extended conjugation and thus lowers the transition energy and shifts absorption towards longer wavelength. What is the role of auxochrome? Role of auxochrome is to render its lone pair of electron in the conjugation. Let's see an example. In benzene ring, benzene itself absorbs radiations, ultraviolet radiations at 254 nanometer, but when the auxochrome NH2 is attached to it, this NH2 gives lone pair of electron to benzene ring. The lone pair of nitrogen comes in conjugation with benzene ring and thus it extends the conjugation and thus lowers the transition energy and absorption maximum goes to longer wavelength. Benzene itself absorbs at 254 nanometer while aniline absorbs at 280 nanometer. These are the two basic terms in ultraviolet spectroscopy. First one is chromophore and next one is auxochrome. Remember the difference. Chromophore is unsaturated species which absorbs ultraviolet radiation. Auxochrome is not unsaturated species, it is saturated species which itself doesn't absorb the radiation, but when attached to a chromophore or a chromogen shifts the absorption maximum value towards longer wavelength. Now let's see what are the shifts in the lambda max absorption maximum. First shift is bathochromic or red shift. What is bathochromic shift? The shift of absorption band to longer wavelength is called as bathochromic or red shift. For example, if a compound absorbs at 250 nanometer and after insertion of auxochrome it absorbs at 300 nanometer, that means your absorption band is shifted towards longer wavelength. Such type of shift is called as bathochromic or red shift. Let's see again, the shift of absorption band towards longer wavelength is called as bathochromic or red shift. Now, how this bathochromic shift can be observed? If you attach a auxochrome to a chromogen, then conjugation will take place and shift of absorption band towards longer wavelength will takes place. See the example of nitrobenzene and paranitrophenol. When the auxochrome OH is attached to nitrobenzene, the lambda max gets shifted from 268 nanometer to 318 nanometer. Such type of shift from shorter wavelength towards longer wavelength is called as bathochromic shift. Now, what is the next condition? When surrounding medium is changed, example, para-nitrophenol, if we add alkali or if we produce an alkaline medium, if base is added to that, abstraction of proton takes place. The lone pair on oxygen immediately bring about conjugation with the benzene ring and absorption maximum gets shifted from 255 nanometer to 265 nanometer, that is bathochromic shift occurs. This is because conjugation in phenol is overpowered by conjugation in phenoxide ion. Phenoxide ion radially undergo shifting of electrons, lone pair of electrons present on oxygen in the benzene ring. Now the next shift is hypsochromic shift. The shift of absorption band towards shorter wavelength is called as hypsochromic shift, which is also called as blue shift. It is noticed when positive charge is introduced in the molecule. If you add HCl in your aniline, then positive charge gets developed on this nitrogen and hypsochromic shift is observed. Initially the absorption maximum was 280 nanometer. It gets shifted towards shorter wavelength, that is 265 nanometer, because in aniline initially there was conjugation of lone pair of nitrogen in the NH2 group with the benzene ring. But as soon as we add HCl, that is acidic medium, to this, then lone pair on this nitrogen, they are masked and positive charge gets on nitrogen. Now there are no electrons on nitrogen for conjugation with this benzene ring, and thus the absorption maximum gets shifted from longer wavelength to shorter wavelength, and such type of shift of absorption band towards shorter wavelength is called as hypsochromic shift. Next one is hyperchromic effect. It is increase in intensity of absorption maximum. Intensity of peak get increases. Such type of shift, such type of effect is called as hypochromic effect. And last effect is hypochromic effect, in which it is decrease in intensity of absorption maximum. Initially the intensity was good, then the intensity of your absorption maximum or absorption band decreases. Such type of effect is called as hypochromic effect. We have seen 4 shifts. First one is bathochromic, second one is hypsochromic, third one is hyperchromic, and last one is hypochromic. Thank you.